Hey everybody, so good news. I believe that I have fixed the issue with the audio and video not syncing up. So now the video should hopefully be a little bit better than what we were dealing with before. So also good news, we are going to be doing L'Hopital's rule. And once you see what L'Hopital's can do, I think you're going to be very happy with it. We're not going to worry about this final point quite yet. That's going to actually happen then in the next video. But we will do the first 3 points then for today. L'Hopital's rule then is going to be related to limits, so we're going to return back to those. Remember that any limit equal to 0 over 0 was indeterminate, and the meaning or indeterminate is just that we have multiple rules of math that are going to conflict. So whenever we had that happen, what we needed to do was we had to simplify our limit. This one right here in the middle, remember that we would factor the bottom. We get x plus 2 and x minus 2. Then we saw that the x minus 2's would cancel. We would put 2 in for x, and we would get 1/4 as our answer. Well, now we've got a better way that doesn't involve simplifying, or I guess it would be simplifying in a different way. So, L'Hopital's rule, here is the proof. What we're going to do is we're going to start with our limit, and we need to have a fraction, f of x over g of x. And then what we're going to do is we are going to subtract f of a from the top, and we're going to subtract g of a from the bottom. And the reason that it's going to be okay that we're doing that is because we're going to say that f of a is equal to 0. We're also going to say that g of a is equal to 0. So that's why it's okay for us to be doing that. Then the next step is that we are going to divide both the top and bottom by x minus a. And of course, that's because x minus a over x minus a is going to be equal to 1. Then we're going to take this, we're going to take this one limit and we're going to split it into two limits, limit of the top and limit of the bottom. And hopefully you recognize that right there is the definition of the derivative, and right there is the definition of the derivative. And together, that gets us then to our final answer, which is that we have f prime over g prime. So that is L'Hopital's rule. If we can show that a limit of f of x over g of x will be indeterminate, f of x and g of x are both differentiable over the interval where x equals a exists, and then the denominator of our derivative is not 0, then this right here, we can just take the derivative of the top and the bottom of our fraction, and that will get us the same answer as before. Now, before we get into any questions with L'Hopital's rule, I just want to point out L'Hopital's is not the quotient rule. We are going to be doing the derivative of the top of the fraction and then the derivative of the bottom of the fraction. There is no f prime g minus g prime f over g squared. We are not doing that. The exception, though, is going to be in an example like this here, where the top does require a quotient rule. However, the bottom, the derivative of sine, is just going to be cosine. We're not going to get sine squared in the denominator here. Now, before we solve any of the questions, I just want to point out this note that I put at the bottom. And that note is that we need to show that a limit is indeterminate first before we solve it. So in the first one, we need to start by just showing, well, 2 minus 2 is 0. 2 squared minus 4 is also 0. And because we were able to show that, now we are allowed to use L'Hopital's. For this note down here, on a multiple choice question, it really does not matter for us, but on the free response, your work is going to get graded on a free response question, whereas your work can't be graded on a multiple choice question. So that's why it's important to show it, just in case. So anyway, now that we have shown this limit is indeterminate, we're going to find the derivative of x minus 2, and then we're going to find the derivative of x squared minus 4, and now we're allowed to put 2 in. we're going to get 1 over 2 times 2. And this first limit simplifies to be 1/4. Now we're going to do the second one. We're going to put 0 in for sine of x, or 0 in for x, I should say, and sine of 0 is 0. The denominator x gets replaced by 0. That, again, is indeterminate. We are allowed to use L'Hopital's. So we're going to do derivative of the top. That's cosine of x. Derivative of the bottom is 1. If we put in 0 for x, we get cosine of 0 over 1. That ends up being 1 over 1. And the answer for our middle limit is 1. Okay, and then for the last one, we're going to put 0 in for put 0 in for x, and then we're going to get e to the 0 on bottom. Now on the top, well, this looks kind of interesting. I think you were expecting that we would get 0 over 0, but cosine of 0 is actually 1. And on the bottom, e to the 0 power is also 1. This question I put there on purpose. No L'Hopital's necessary. Because we were able to solve it without getting an indeterminate form. Now, I do want to show you quickly, though, in case you do think that you could have solved it with L'Hopital's anyway and you were trying to get the derivative, let's just demonstrate that. Let's pretend we didn't know it was indeterminate. We went ahead, we found negative sine of x on top, we found e of x on bottom. If we put in 0, then we get 0 over 1, and we're not supposed to have 0 because we've already demonstrated that the answer was supposed to be 1. So that's why we could not have done L'Hopital's in order to solve the last one. It doesn't even get us the correct answer. So that's very important. Just make sure that you need to show it's indeterminate before you try to do L'Hopital's. Okay, so for all three of these then, pause the video, give them a shot, and when you are done, I will demonstrate how to solve these. Okay, for the first one, as I said before, make sure you show that you have an indeterminate form. 2 times 0 is 0. Arctangent of 0, that is going to be 0 as well, so we can use L'Hopital's. Now we are going to find the derivative of the top and the bottom. Derivative of the top is 2. The bottom, make sure you remember your derivatives of inverse trig functions. It is 1 over 1 plus x squared. Now we can put in 0. We're going to get 2 over 1. And the answer for our first limit is 2. Alright, for the second one then, if we put in 0 for x, sine squared of 0 is going to be 0. Down at the bottom, x gets replaced by 0. That is indeterminate. We can do L'Hopital's. Now, for the top, before we attempt to get its derivative, it may be useful just to rewrite it into a form that's a little easier for us. Some of you may not remember how to get the derivative of sine squared, so let's rewrite it as sine of 4x squared before we find its derivative. Because now we can see a little bit more easily that we need to do two chain rules. We're going to do power rule first, so we're going to get 2 times sine of 4x. Now we need to do the derivative of the inside, which was going to be cosine of 4x. And now the inside of that times 4. And then on the bottom, it's just going to be 1. Now, actually, you know what? We don't need that limit anymore because we can just put 0 in for x. We're going to get, and I'm going to do a little bit of simplifying, 8 sine of 0 cosine of 0, which is going to turn to 8 times 0 times 1. And the answer here for B is 0. Okay, now for part C. As usual, put in our values. Natural log of 1, that is 0. On the bottom, 1 minus 1, also 0. So we can do L'Hopital's. We need the derivative of the top first, and we're going to get 1 over x. On the bottom, the derivative is just 1. So when we put in 1 for x, we get 1 over 1, and the answer there is 1. Now, 0 over 0 is not the only indeterminate form that we have. We actually have quite a few others as well. So I am going to give you an explanation as to why all of these are considered to be indeterminate as well. And remember that indeterminate means that there are multiple rules of math that conflict with each other. We're supposed to get different answers, but because there's more than one possibility, the answer actually does not exist. So for the first one, if we have infinity over infinity, well, the numbers are supposed to be the same, so that suggests the answer is supposed to be 1. Sorry, that's a bad question mark. That's a question mark. But then we also are supposed to know that infinity divided by anything is positive or negative infinity. And then if we take anything divided by infinity, that's supposed to be 0. So we have 3 possible answers, actually I guess 4 for positive and negative infinity. We have 4 different answers that we could consider, so that's why that one is indeterminate. For the second one, 0 times infinity. Well, 0 times anything is supposed to be 0, and then infinity times anything is supposed to be positive or negative infinity, so that is going to be indeterminate. For the next one, infinity minus infinity, if it's the same thing minus itself, that's supposed to be 0, but infinity minus anything should be positive infinity, and then anything minus infinity is supposed to be negative infinity, so therefore we have multiple possible answers. That is indeterminate. 0 to the 0 power. 0 to any power is supposed to be 0, but then anything to the 0 power is 1, so that one will be indeterminate. Now this next one, I've had some people, mostly students I should say, disagree with me that this counts as an indeterminate form, but it does. The reason 1 to any power is supposed to be 1, but then anything to the infinity power is supposed to be infinity, so therefore that has to be, that one does not exist, it can't exist, so that has to be indeterminate. And then finally, our last one, infinity to the 0 power. So infinity to any power is supposed to be infinity, but then anything to the 0 power is 1. So you need to recognize all of these forms before you do L'Hopital's. So yeah, there are going to be many different ones that we could see. Just so you're aware though, I don't want you to freak out, because really the most common ones, oops, that's a bad circle. The most common ones are going to be those. If I were to pick another one also, I would say probably that one. So green is most common. Okay, so one other important thing to note about L'Hopital's rule is that we can do it multiple times for the same limit. Now, when I was making my, when I was practicing these questions earlier, I noticed that actually one of these, you don't need to do it multiple times, but for the other one, you definitely will. Remember that what we need to do first is we need to show that we get an indeterminate form. So I'm going to just do my work down below. If we put in 0 from the right-hand side into this fraction, well, we remember back from term 1 that 1 over 0 from the right-hand side is supposed to be equal to positive infinity. And then e to the infinity power is infinity. Then, for the bottom, we've already done 1 over 0 from the right-hand side, so that also is going to be positive infinity. Therefore, we have an indeterminate form. It's one of the new ones I just showed you on the last slide. Now we can go ahead and do L'Hopital's. And the derivative for e to the power of 1 over x, I'm going to do this down here below just to give myself a little bit more space to show you. Remember, derivative for e to any power, we recopy what we've started with, and then we have to do the derivative of the exponent. Hopefully you can remember now that the derivative of 1 over x is negative 1 over x squared. If you don't remember that, we can do it like this. We got negative 1x to the negative 2, and that becomes that over there. So we can go ahead, write that on our top. We've got negative 1 over x squared times e to the power 1 over x. Then our denominator, well, we've already figured out that the derivative of 1 over x is negative 1 over x squared, so we can just go ahead and write that. Now let's not put anything into this limit. Let's actually do some simplifying, because we have 1 over x squared on top and bottom. Well, and they're both negative, so those negatives will cancel too. That leaves us then with just e to the power 1 over x. And we already demonstrated earlier this right here. When we put in 0 from the right-hand side, it's equal to infinity. So our value for this first limit is positive infinity. Now, in the second question, you may remember back from term 1 that I showed you that if you look at the degree of your polynomial, and if they are the same, then the answer is going to be just the ratio of the leading coefficients. So back in term 1, we already knew that the answer for this was going to be 3 over 2. Now with L'Hopital's, we have we can justify why the answer is indeed 3 over 2. Once again, let's start by putting in infinity. So in the first one, it would be infinity plus infinity minus 4. That is just going to be infinity. On the bottom, infinity minus infinity plus 1. The plus 1 doesn't matter. Infinity minus infinity is going to be indeterminate on its own anyway, but that's how we know then that we cannot solve this. So we're going to need to use L'Hopital's. We're going to take the derivative of the top and bottom, and the top is going to become 6x plus 1. The bottom will be 4x minus 2. We should check to see if we can solve this. Up on the top, we're still going to get infinity plus 1. On the bottom, infinity minus 2. So infinity over infinity is pretty much what we have. It's still indeterminate. We need to do L'Hopital's again. Now the derivative on the top is going to be 6. The derivative on the bottom is 4. There's no x for infinity to go in. And that simplifies to be 3/2, just like we knew back from chapter 1. Okay, so I want you to try these 3 limits on your own then. Some of them will need L'Hopital's multiple times. There is the possibility also that you may not need to do L'Hopital's to solve them. So pause the video, try these on your own. When you are done, I will demonstrate how to get the answer. All right, for the first one. So we are going to need to show that it is indeterminate first before we do L'Hopital's. Now, we need to first get tangent of pi over 2 from the left-hand side. Sorry, not -1 from the left-hand side. And if you don't remember what that is, it may be helpful to use the graph of tangent. And tangent has an asymptote at pi over 2. And if we're doing it from the left-hand side, well, that's this part here. We know that that is going to be positive infinity. Now we have to do secant of pi over 2. And again, from the left-hand side. So we know that secant is the same thing as 1 over cosine. And cosine of pi over 2 is 0. Oh, I keep writing -1 here. We know that it's going to be 0. And one other thing as well is that from the unit circle, if we're approaching from pi over 2 from the left-hand side, well, that means value is less than pi over 2. And over here, cosine still would have been positive. So that's going to be positive 0 there. And we know that 1 over 0 from the right-hand side is going to be positive infinity as well. So we get infinity over infinity. We are allowed to do L'Hopital's. Now we need to find the derivative of the top. And derivative of tangent is going to be secant squared. Then on the bottom, we need the derivative of secant, which is going to be secant tangent. And I noticed that we are able to cancel one of the secants on top and the secant on the bottom. Now we're left with secant over tangent. And we should go ahead and simplify this a little further. We know that secant is going to be 1 over cosine, and then tangent is going to be sine over cosine. So let's break those up. Because we're going to see that we can cancel cosine from the top and bottom. They both fractions have cosine as a denominator. Now we're left with 1 over sine. And I think just to keep it easy for us, we're going to keep it as 1 over sine. And then we will need to figure out what is sine of pi over 2 from the left-hand side. Sorry about that. I am not giving myself enough space here. Okay. So it may be beneficial for us just to go back to the unit circle again. Pi over 2 is right here, and we are approaching from values that were less than pi over 2. So that is where we're coming from. And we know that sine at pi over 2 is going to be 1. And if we're approaching, we're getting really, really close, well, it's going to be going towards 1. So that means that this is equal to 1 over 1. And the answer for our first question is going to be 1. Okay, give ourselves some more space then so we can answer the other questions. For the second one, we're going to start by putting infinity into both. The top, e to the infinity, is indeed infinity. At the bottom, infinity to the 4th power, that will be infinity. We need to do L'Hopital's. Alright, so we will go ahead. Derivative of the top is going to be just e to the x. On the bottom, we will get 4x cubed. We need to put infinity in for both, and we're going to get infinity on top and bottom, so we have to do L'Hopital's again. And in fact, I can already see we're going to have to do L'Hopital's many times here. Fortunately, if you ever have to do L'Hopital's more than once, usually you only have to do it twice. If you do have to do it many times though, typically all of your derivatives are going to be pretty simple, like this example. Oops. And at least we're getting towards the end now. Kind of interesting how we only have e to the x the entire time on top. We eventually get to infinity over 24. And so that middle limit, its answer ends up being positive infinity. Okay, then for our last one. If we put in pi for each of these, we're going to get, I'm going to do it down here just for right now. Whoops, sorry. Natural log of sine of 2 pi. Well, the natural log of sine of 2 pi, that is going to be natural log of 0. And I don't know if you recall this. We do say that natural log of 0 is going to not exist, but, and I think we probably should have had maybe a little bit more information in this, but this is the graph of natural log down here. And at least from the right-hand side, we can see that it goes down to negative infinity. So we could say that then for the top. Now the exact same thing is going to happen down on the bottom, because sine of 2x and sine of x, when we put in pi, it doesn't matter. Sine of pi and sine of 2 pi are the same thing. They're both 0. So we're going to get negative infinity over negative infinity, and that shows then that we will need L'Hopital's to solve this question. Okay. Then we will go ahead and take the derivative of the top and the bottom. So for the top, I'm going to do the work just kind of a little bit lower first, and then we'll write in our new limit. So the derivative there, it's going to be 1 over sine of 2x then we need to multiply by the derivative of sine, and then lastly we still need, I'm kind of out of space here, we still need to multiply then by the derivative of the inside of cosine, which is times 2. So that means that for the top, we are going to get then, if we choose to simplify, and actually I'm not going to turn that into cotangent, I am going to keep it as 2 times cosine of 2x over sine of 2x. Then the next part that we need is to find the derivative of the denominator. And it's going to look very similar to what we just had on the top. Fortunately, we won't have as many chain rules to do. So we know that natural log of sine of x, its derivative will start as 1 over sine of x. And then after that, multiply by the derivative of sine, which is going to be cosine. Once again, I am not going to simplify that into cotangent. I'm going to keep it as cosine of x over sine of x. We have a lot that is going on here now, and I am not going to try to put pi in, even if you, well, you know, I should demonstrate it. If you put in pi, what you're going to get is 2 cosine of pi, 2 pi I should say, over sine of 2 pi, and then all of that over cosine of pi over sine of pi. What's going to happen when we try to simplify this is that we're going to be able to get 2 times 1 for cosine of 2 pi times 2. Sine of 2 pi, though, is 0. Then down at the bottom, cosine of pi, what we're going to get is 1 sine of pi, that is also 0. I'm sorry, cosine of pi is negative 1. We can't solve this yet. We're divided by 0 in both the top and the bottom. So we do need to do some more work. You may initially be thinking then, oh, that looks like that was indeterminate, so we should go ahead and do L'Hopital's a second time. I'm actually going to discourage you from doing that. Instead, what we're going to do is we're going to take this fraction, and instead of dividing by that fraction, let's multiply by its reciprocal. So let's have limit as x approaches pi. We're going to keep 2 cosine of 2x over sine of 2x. But now, let's multiply by sine of x over cosine of x. And I see something else that we can do as well. Down on the bottom, sine of 2x can be simplified. I don't know if you remember, but back from IM3, you learned about the double angle formulas. And we can make sine of 2x turn into another value. So what I'm going to do, I'm just going to zoom in a little bit just because it's going to get a little tight, so it's easier when I can do this. Up on the top, I am not going to change anything. 2 cosine of 2x times sine of x. Down on the bottom, though, sine of 2x can change into 2 sine x cosine x. And then this cosine comes at the end. Now what I see is that there's a sine of x that cancels from the top and bottom. And we finally are getting to a point where we are going to be able to solve this. If I put pi now into everything that remains, we're going to have 2 times cosine of 2 pi over 2 times cosine squared of pi. Up on the top, that becomes 2 times 1. On the bottom, oh, I'm sorry, I should have canceled these 2's. Let's get rid of both of those. So let's not have those anymore. Let's not have those anymore. Let's just have 1 on top. And then on the bottom, that is going to become -1 quantity squared. And finally, we have our answer, which is +1. All right, we do have a little bit more to do, but fortunately, it's going to get easier than what that last question was. So, L'Hopital's, I mentioned this earlier, and I'm going to go back up just to show you again. For L'Hopital's, we must have a fraction. If we do not have a fraction, then L'Hopital's is not possible. However, we can cheat a little bit, and we can turn what is not a fraction into a fraction so that L'Hopital's does become possible. And I'm not even saying x over 1. I'm not saying natural log of x over 1. That wouldn't be good anyway. Instead, what we're going to do, it's kind of like what we just did in the last example where I took cosine over sine and I multiplied by its reciprocal. We're going to do the same thing here. We're going to take this x and turn that into its reciprocal. And then we're going to divide natural log of x with that. So our first step is going to be to turn this into, so first limit as x approaches 0 from the right hand side. And we are going to have natural log of x divided by 1 over x. Now, I suppose we should have checked to see if we were going to have an indeterminate form first. We still could check right here because we haven't done L'Hopital's yet. It's perfectly fine. But I'm going to choose just to show it here, just so at least you can see a different indeterminate form than what we've had before. So in this case, if we put in 0 for x, we have 0. If we put 0 in for the natural log of x, that becomes -infinity. And so that is an indeterminate form. If we had chosen to do it here, kind of a similar thing, except this time now in the bottom, what we're going to get is 1 over 0 from the right-hand side, and that's going to turn into positive infinity. So either way, we would have had an indeterminate form, whether we did it with the very first limit or if we did it with our second limit. Regardless, now that we've shown that we have an indeterminate form, we can go ahead and find our derivative. So doing L'Hopital's, we're going to get 1 over x on top. On the bottom, what we will get is -1 over x squared. And let's go ahead. I think some of you might see how this would simplify. We could cancel x from top and bottom. If it is easier, though, just multiply by the reciprocal of the denominator. We could just write it like that. And now I think it might be easier to see that we can cancel an x from top and bottom. Now we are going to have -x, just -x actually. And that means that our answer for this is going to be 0. So we are at our final slide. I want you to try this one. Pause the video and when you are done, I will demonstrate how to solve it. All right, so I am hoping there's a couple different ways that you could solve this, but there is definitely an easier way and there's definitely a harder way. The easier way is going to be if you decide that e to the negative x is going to move to the denominator. The harder way would have been if you had chosen that x was going to move to the denominator. So what we should do first is we should go ahead, show that this is going to be indeterminate. So if we put it in infinity, we're going to get infinity times e to the negative infinity, which then if we simplify that, we still have infinity e to the negative infinity. Be careful with that. That's 1 over e to the infinity becomes 1 over infinity becomes 0. We would have infinity times 0. So yes, that is indeterminate. So we should go ahead then and turn this into a simplified form that allows us to do L'Hopital's. So I'm going to take the x and keep it on top. And if we move e to the negative x to the bottom, it becomes e to the x. And I think you should be able to see here why this was much easier. Now, we have to do the derivative of the top and bottom. We're going to get 1 on top, e to the x on bottom. This turns into 1 over e to the infinity. We're going to get 1 over infinity. And the answer for this was going to be 0. All right, that is everything. So again, L'Hopital's is one of the most useful things that you are going to learn in calculus for the entire year. Go to Schoology. I'll let you know which questions are required and which ones you can skip. Thank you for listening, everybody.